Okay, so as we saw this morning, physicists have a long-standing fascination with cats since Schrödinger till this morning. So what I'll discuss today is
This morning we had a mouse.
we had some remnant of the Cheshire cat. And of course, mice and cats are strongly entangled, as anyone who saw enough cartoons know. So what I'll do today is try to convince you that using entanglement properties of quantum systems is actually a very useful way to extract information about different quantum phases that interest mainly condensed matter physicists, but also other physicists. And we can use it as a new tool to characterize and understand properties of quantum phase transitions. And I'll concentrate on a particular quantum phase transition, the disorder-driven Anderson phase transition. So just interestingly, there was a lot of discussions on what you can find on Google nowadays. So if you'll just, well, actually it's 2 years ago, if you'll just type in image of a mad scientist, I got this picture, which part of it makes totally sense. As we know, all mad scientists have long white hair. Most theorists, when they go and write equations on their blackboard, wear white lab coats. But the interesting thing is that actually what he's writing is not the expected E equal mc squared, which is a staple of any equations that non-scientists know, but it's actually the matrix product state that I'll show you in a moment. Okay, so what's entanglement entropy, or in general, how can we measure entanglement between two parts of a many-particle system? So basically, we divide the system into region A and region B, and assume or define the system exists in some pure state psi of the whole system. Of course, in that situation, if we want to separate the basis of the two different regions A and B, the most general things that we can write is some external multiplication of the basis in A and basis in B, and in general, we should have here some matrix alpha ij that actually defines the wave function. Interestingly, for any given psi, pure state psi of the whole system, we can actually perform the Schmidt decomposition, which says for each psi we can choose an appropriate basis in A and B, where this matrix is actually diagonal. And basically, if we'll think about it, if we're writing the reduced density matrix of region A, meaning we trace out the degrees of freedom of region B or vice versa, this coefficient alpha square is just the eigenvalues of this reduced density matrix. The sum of it is just 1 by construction, the sum of these eigenvalues. Now, the general definition of entanglement entropy is just as Shannon or information portrayed by these eigenvalues. It's just the usual von Neumann or Shannon entropy of this eigenvalues. And if we think about it, if the two states are if the two regions are completely disconnected, we'll have a situation where we have only one value there, and therefore the entanglement entropy will be 0. If we have a lot of connections between these two regions, these will have more or less a distribution of these eigenvalues, and we'll end up with some finite value of the entanglement. And there are also other measures like the Rényi entropy that turn out to be very useful. Okay, another concept that I would like to introduce was given by Haldane a few years ago, which basically talks about the entanglement Hamiltonian. And the concept is, since we have a density matrix, and we know that classically, if we want to write down a classic density matrix, we just give weights to all the states of the system just according to some thermodynamical definition. And if we assume that we can get the eigenvalues of the density matrix out of some fictitious or constructed Hamiltonian, we'll have this simple relation, assuming that we have a temperature that we define as 1. So the logarithm of these eigenvalues gives us the entanglement spectrum as they defined it. Okay, another point that one has to note is that for this entanglement spectrum, actually for most cases that we will consider here, the number of particles in a region is a good quantum number. We are talking about a pure state in the whole system. Therefore, we have NA and NB particles in each part of the system. And we can label even which eigenvalue of this reduced density matrix belongs to which number of particles in this subregion A. And we can also define an entanglement level spacing. Okay, so what do we do with all these definitions? The philosophy is quite simple. If we're looking on this entanglement properties, it tells us basically how region B influences region A. And this influence exists along some finite correlation lengths. And as we know in quantum phases, the correlation length is one of the most important parameters that we are looking into. So if the correlation length is infinite, we have influence on region A from region B for very long distances. If it's finite, let's say in a gapped phase, or in the case that I'll show you where we have a localization length, we'll see it only on a distance psi from the boundary. Okay, so what is the connections between the entanglement spectrum and condensed matter physics? One of the oldest connection is actually one of the most useful many-body numerical methods that we have. It's the density matrix and normalization group, which actually tells us, instead of the usual ways that we do renormalization group where we keep low-lying states, here we keep strongly entangled states in this procedure. Another thing is at the quantum phase transition and around it, we'll have different behavior of the entanglement, and we can use it to characterize the quantum phase transition. And as I said, as I emphasized previously, the fact that the correlation length may be finite at some quantum phases, we can use the entanglement properties in order to measure this correlation length. Well, the simplest way to measure this correlation length would be to use directly the definition of the entanglement entropy. Now, the ground state entanglement entropy behaves according to the area law, which is the linear dimension of region A to the power d minus 1. For a one-dimensional system, of course, that will be just constant, but we know that if we have an infinite correlation length, there will be also some logarithmic correction. If we have some finite correlation length, we expect the entanglement to saturate on the level of on the length scale of Xi. Okay, to be specific, I'll look on a specific Hamiltonian, which is a very simple Hamiltonian. We have here just a tight binding model of one-dimensional system, of one-dimensional fermions. To simplify things, I'm considering here even the spinless case. There's some on-site disorder which comes in from a distribution of these on-site energies. And I have nearest neighbor interaction when I'm saying here that I'm partitioning the system to two different regions, A and B. So I mean the thing depicted here in this figure. And another useful characterization is, in order to put some measure of the disorder, I distribute the on-site energies in some box distributions between minus WT and W over 2, and I have the Luttinger parameter which characterizes the strengths of the nearest neighbor interactions. What is the localization length in the system? These are well-known results. The influence of disorder, of course, when W is 0, no disorder, all the on-site energies are the same. It's infinite. For some finite widths of the distribution, it has some finite value. And we know also to incorporate the influence of interaction into the system. Just to give you a feeling, since we are always dealing here with finite-sized systems, although very large, the largest system here is of size 1,500 with 750 electrons, so it's a quite big system for a full many-particle calculation. It depends, of course, on the total length of the system, that's the finite size effects, and the size of region A. And we can see it behaves logarithmic as long as I'm not too close to the middle, and then there's some finite size effects, but the logarithmic description works very well for clean systems. I put in disorder, and I see that the entanglement entropy saturates, and basically I can just very simply read off the localization length, which I calculated using the previous distribution, just off this figure of the entanglement entropy. And we can see that once the system is larger than the entanglement entropy, the fact that I have longer systems doesn't make any difference, because we have just a finite region where it entangles and then it saturates. Actually, one could pull out through those fits of the entanglement entropy that you calculate numerically, pull out the whole dependence of the entanglement entropy on of the localization lengths on interaction and disorder. It works pretty well. Another thing is just look at on a much simpler property of the system, just the first level spacing in the entanglement spectrum, which is just one number. The second level minus the first level. And we can see here that if we change disorder or change interaction, at the beginning, we have a strong dependence of this first level spacing as function of the distance LA from the end of the system, but then it saturates. And it saturates for the same reasons that we saw the saturation in the entanglement entropy. Simply, once psi becomes smaller than LA, we stop to see any influence of how big is region A. It depends just on psi, and that's why we see here these saturations. Actually, you can pull in even more exact data out of it, and simply, well, like in any particle in the box, you assume that delta 1 will behave like 1 over psi, the length scale of this box. You have here another point that you have to pay attention, which is the fact that you couple only between states that have the same number of particles in region A. Therefore, you have to see also the variation in the number of particles in region A, which turns your dependency instead of 1 over psi to 1 over square root of psi. Take all the information, average information that we had on the first level spacing as function of W, and for the non-interacting case, we have here perfect fit to this type of 1 over W, 1 over the square root of psi dependence. Once interactions are taken into account, we seem to lose this straight line, but that's completely what you expect, since you have to take into account also the influence of interaction. And if you take into account this influence of interaction, meaning you scale it as 1 over 3 minus twice the Latinger parameter, all these curves fall on a very nice fit, and even you get the expected broadening of the width of this level spacing, which should be linear in use. Also, you get it here in the prefactor of this fit. So you can pull out pretty much information out of the entanglement spectrum. Okay, but all this is in the localized regime. How can you put into this system a phase transition? If you look on attractive interactions, if you have attractive interactions, then you have a transition into a superconducting behavior, and then psi diverges. In this case, if you put in attractive interaction, k becomes larger than 1, and then we see that when the value is 1.5, we have here a divergence of the correlation length of the localization length. Okay, but in that case, if we have a divergence in the correlation length, looking at the saturation of the entanglement entropy or the first level spacing, the things that we did previously, will be a very poor way to characterize the phase transition point, for the simple reason that your system is always smaller. However big you are taking your system, once you're getting close to the transition, psi will just shoot into a longer length scale, and you won't be able to see exactly where the phase transition occurs. Here, actually, you can be helped by the distribution of the entanglement entropy. Entanglement entropy in a disordered system, of course, fluctuates from realization to realization and from a point LA that you cut it to a different point. So basically, if I look on the average entanglement entropies, both regions here are very similar. But if I look on the distribution of this entanglement entropy in the insulator regime, although this is insulator just by name, it's just much smaller than sizes. So in principle, it's showing metallic behavior. It's just Gaussian. Once we are going into the superconducting regime, we have a very strange skewed distribution. And actually, it's a very interesting distribution. This is a Levi-Stable alpha distribution, which people see in all kinds of fields like finances and things like that. In physics, it's very hard to find simple systems like the ones that I described, which give you this broad and power law tail distribution. Okay, I'm running out of time, so I won't go into many details. So I hope I convince you that you can use entanglement properties into characterizing the Anderson localization, and I left this open as we have many other systems which we can use this quantum entanglement in order to characterize quantum phases and their behavior. So, thank you.